Hey, in 1991, the post office issued a stamp that's pictured up here. And if you look behind the X's, it says, Pluto not yet explored. So at that point in time, Pluto was the last planet that we have not yet sent a satellite to. So in 2015, when the flyby happened, the New Horizons team made a blow-up of that stamp and crossed off the not yet. So it was a big moment, kind of a neat way to celebrate that. So for tonight's presentation, we're going to look at the discovery of Pluto. We'll look at what it took to pull together the mission, and then some of the things we've learned from the flyby. So Clyde Tombaugh discovered Pluto in 1930. He was a Kansas farm boy and also a backyard astronomer, had his own telescope, and he did a lot of sketching. And he knew that Lowell had predicted there was a missing planet. Something was beyond Neptune. And a job opportunity came up in 1928, and he submitted some of his sketches to the Lowell Observatory, and he got the job. So he was now in charge of using their 13-inch telescope to find this missing planet. So he took pictures every night, and he used the Zeiss Link comparator to look for this planet. So if you look at the lower picture in the right, he's there at an eyepiece, and you have a picture on each side, and it lights that picture up for 1 second, and then it turns the other one on for a second. So it's alternating pictures back and forth. And what he's looking for relies on eye persistence. Did he see a little dot that moved against the star field? And in fact, he did in January 1930 see this missing planet. So he went into his boss and he said, Dr. Schleifer, I have found planet X. So if you look where the arrow is pointing, you can see in the middle picture there the two large stars, and then the dot moves to the right of those in the next picture. And these are from the 23rd and 30th of January, so they're 7 days apart. So they discovered it in January, but they didn't make the announcement until March because they wanted to be really sure that they weren't making a mistake. So they did a lot more analysis over those 3 months, and they even had other people look for Pluto to find that it was really where they thought it would be. So the discovery happens in 1930. In 1950, they figured out what the rotation period was. It was 6.39 days. In 1970, we discovered there was methane frost on Pluto. Then we discovered that it had a moon called Charon. Turns out it goes around Pluto in 6.39 days. It's going to be an interesting number. Then in 1985, Charon started eclipsing in front of Pluto. And from that, we can tell that Pluto had an atmosphere of some kind. Then they found Charon was made of water ice. And in 1989, with all of this information, the mission was proposed. And in 2001, the Applied Physics Lab was given the mission. So notice there's 12 years there. To get a mission approved at NASA is not an easy thing. Every year a committee meets and everybody sends in their proposals. You have to be the top pick in order to be funded. So there was a lot of letter writing campaigns by astronomers trying to get this mission approved. This is before the internet and email. It was approved along the way, and then it was defunded at one point, and then all the scientists got upset, did more letter writing, and finally it happened. And so in 2001, Applied Physics Lab was awarded the contract. So the launch date was in 2006, so that's 5 years to design a spacecraft and build a spacecraft and launch it. Now, it's going to take 9.5 years for this spacecraft to get to Pluto. If you can't launch in 2006, if you wait till 2007, it's a 14-year trip. So they were really under the gun. They built a new third-stage rocket for this that had never been used before. The Applied Physics Lab was the first lab outside of JPL to get a contract like this. So they had a lot of new ideas and a lot of things they had to build and improve. A lot of instruments were on here that had never been used before. It had nuclear power, so that's a whole approval process you have to go through as well. So January 9 comes along, there's the launch, and there's actually what New Horizons looks like. This was the fastest object to leave the Earth. When it launched, it was moving 36,000 miles an hour. The International Space Station and other satellites in low Earth orbit go around the Earth at 17,500 miles an hour. So it was moving pretty quick when it left. So here's some facts about Pluto before we got there. That's the best picture we had at the time. That's from Hubble telescope. And you might say, wait, the Hubble telescope, it's a big telescope, it's pretty amazing the pictures you get. Well, Pluto is so small and so little light reflects off it that you just can't get a really good picture. It's very cold there. And there's that 6.39 Earth a day rotation. It takes 248 years for it to go around the sun. And it's only 2/3 the width of the United States, 1,400 miles wide. Pretty small object. It orbits 3.6 billion miles away. The Earth is 93 million miles from the sun, so Pluto's way, way far away. And at the time of the launch, we knew there was one moon. Now there's 5. We'll get to that in a minute. So what's really interesting about Pluto and Charon, if you're standing on Pluto, if you're the blue person, and the blue person over there on Charon, as Charon goes around Pluto, those two blue people are facing each other the whole time. It's a phase-locked orbit. So Pluto rotates in 6.39 days, Charon goes around in 6.39 days, so it's always the same face pointing at Pluto. Something unexpected. There's a size comparison for you. So there's the Earth, Pluto, and Charon. Now, most satellites, most moons that go around planets are less than 10% the size of the planet they're going around. Another surprise. Charon is much bigger than that. It's going to affect the orbit and how things orbit. We'll see that in a minute. So, 2006 is the launch. In 2007, we do the Jupiter gravity assist. That's why we wanted to leave in 2006. Because if you left in 2007, you didn't get the Jupiter gravity assist. So as you go around Jupiter, you're now going 52,000 miles an hour. And then we're getting close to the flyby, and 10 days before the flyby, a total loss of signal. Now that signal takes 4.5 days to get to Pluto, and 4.5 days to get back. So they had to upload all the plans ahead of time, and now they can't even communicate with the satellite. 10 days before the flyby. You can't stop the flyby. 52,000 miles an hour, it's going by Pluto at a certain point in time, and we can't stop and make up for it. It's a one-time shot. So, it turns out they were downloading some initial pictures, and at the same time they were uploading the plan for the flyby. Now, while it was going to Pluto, they spent a couple years figuring out when to turn all the cameras on and all the other pieces of equipment to get the data they wanted. And they had to be very precise. Although it took 9.5 years to get there, we're going to kind of use an analogy here. Hitting the window to get the data you wanted at Pluto was like flying from Chicago to LA and landing within 40 milliseconds of your prescribed landing time. That's landing within 40 thousandths of a second. So this was one of those events that you had to plan it and it had to go just right. So between the 4th and the 14th, a lot of people lost sleep. They were working 3 and 4 days in a row. They finally figured out what happened. They had the signals coming down and signals going up. They kind of shut the computer down and overwhelmed it. They got the signal back. They loaded up the new plan because they had to adjust things. And in the end, they lost very little of the data they had planned to get. So absolutely amazing recovery in 10 days. So this gives you a diagram of what the trip looked like. Launching in 2006, going by Jupiter in 2007, getting to Pluto in 2015. And then, of course, the New Horizons continues out of the solar system and into what's called the Kuiper Belt. So these are objects that are very small. There's a field all the way around the solar system. We think these are objects that exist from the formation of the solar system. And here's another picture just to give you a sense of the planning that needs to be done. You can see from the color code how the timing works. Like Pluto at launch was here in its orbit. You had to plan to come by Jupiter at just the right time to get out to Pluto out here and then do the flyby. So, while New Horizons was heading to Pluto, a couple things happened. Anybody know what happened to Pluto? It's not a planet anymore, right? So the powers that be decided it wasn't a planet while we were heading there. But the other thing that happened was there was a fight for a little bit of Hubble telescope time. Another, satellite, the Hubble telescope. Time is very precious. They fought hard. They got some extra time, and lo and behold, they find out there are 4 other moons going around Pluto. They're really tiny. So now there's 6 objects to look at when you get there. So this diagram gives you a sense. I get it to work. There it goes. So look first at Pluto and Charon. Most moons go around the planet they're orbiting with the center of the planet being the point of the center of rotation. But because Charon is so big, they rotate around the center that's between them. And then you have these 4 kind of small, funky satellites here, other moons, especially Hydra. That would probably not be a good place to hang out too long, especially if you don't like rides that spin. So, the Applied Physics Lab, as I said, got this contract. It was the first time some other organization besides JPL had gotten this. So, they had a lot of ideas that went into this that made them win the contract. A lot of equipment that people hadn't thought of before and ways to do things. So, each one had its own name. So, Ralph is the camera system. There were color cameras and infrared cameras and black and white cameras. So you could look at the surface. There was an ultraviolet spectral imager, so you could look at the atmospheric gases that were called ALICE. LORRI was a long-range reconnaissance system. Think of it as a telescope with a camera on it. So those pictures they were trying to download when the whole crash happened, they were pictures that they could get of Pluto early, and they wanted to see what they looked like. You have REX, which is the radio equipment. You can look at temperatures and pressures. SWAP was the solar wind particle. That was measuring the escape rate of the atmosphere. So the sun releases particles that are like a wind that travel through the solar system. And so they're going to hit the atmosphere that's at Pluto. We do have an atmosphere of some kind. And it's going to push them out into space. So this was going to measure that solar wind. PEPSI looked at what was the composition of the particles being pushed off that atmosphere by the solar wind. And then there was one that was designed by students. First time this had ever been done, the student dust counter. So they counted interplanetary dust density. So the last 3 they left on the entire trip. So we now have, for instance, an interplanetary dust measurement from the Earth all the way out. And so those are continuing to monitor as they even go beyond Pluto. The top 4 were only turned on periodically. In the 9.5-year trip, they were only on for 3.5 years. So they saved 6 years of wear and tear by having them on. But again, every time they went to turn them back on, there was that deep breath sense of, is it going to happen or not? Okay, so what did we find? Pluto does have an atmosphere. And if you're standing on Pluto looking up, the atmosphere is blue, just like on the Earth. Absolutely incredible, totally unexpected. And that's because most of the atmosphere on Pluto is nitrogen. So Pluto has an atmosphere that's 90% nitrogen, Earth is 80% nitrogen. There are some other gases, but there's no oxygen there. Enough of the UV rays getting from the sun to Pluto do cause some reactions that will color the surface of Pluto. We'll see that in a little bit. And this atmosphere really does extend 1,000 miles off the surface of the planet. It's not like our atmosphere, it's much thinner. And one of the reasons for getting there sooner than later was because Pluto is going away from the sun in its orbit. It's going to get colder and colder, and eventually they think the entire atmosphere will freeze down onto the surface. So if they couldn't get there in 2006 or 7, they had to leave a lot later, they might have missed the atmosphere analysis. So, as I said, this is the best picture we have from Hubble. That's the picture they got at Pluto. So just stop for a second. You've been working on this for 10 or 20 years and that picture shows up. I mean, it's just amazing. Nothing like what they expected to see. Most people think of Pluto as just a little dark rock out there. And yet it looks like this. So there are nitrogen ice plains there. There are canyons and mountains and polar caps. There are dune fields, and we think of sand dunes. This is going to blow your mind when you see what these dunes really are. There's volcanoes and glaciers, and there's evidence of past liquid flow. So it's frozen now, but sometime in the past, we had movement of nitrogen as a liquid and water as a liquid on the surface. And there's a heart. So that heart shape popped out really quick. And what's really cool, this just happened recently, that is known as Tomball Regio, named after Clyde the Discoverer. And Regio is a Latin word for region, so that's where that comes from. So if you zoom in, you can see in this ice plain, there are movement of these different pieces of ice with these lines through here. You can see them in here. So things are actively still moving on Pluto. That nitrogen ice field is moving around. And there's water icebergs. So some of these bumps that you see, now you have a closer picture coming up, are water icebergs floating on top of frozen nitrogen, because water ice is less dense than nitrogen ice. Again, the image was just this cold, dark rock, and this is what we're finding. So if you look at this picture, you can see things like clusters of hills where you've got water ice, you've got glaciers running here. Looks like this may be a volcano of some kind. So much, much more complex than anybody ever expected for a little old 1,400-mile wide planet. There was more ice there, water ice, than anybody ever expected. So you can see all the blue in that right picture are areas where there's frozen water. So let's go back to those dunes. They're not sand dunes. They're methane dunes. So methane, the gas that makes up, if you have gas appliances at home, that's almost 100% methane that you're burning, okay? On Pluto, it's frozen, and it's in little particles that look like sand, and it's being blown around by the really weak atmosphere on Pluto. Again, totally unexpected. And these dunes and the movement, they're not billions of years old, like a lot of things in the solar system. They're in the decades, or maybe centuries old. Things are still going on Pluto. So here's the big question. Why? Why is all this happening? There's not enough of a kind of a gravitational tidal force between Pluto and Charon to actually keep up Pluto. That's happening around like Saturn and Jupiter with some of its moons, but there's not enough gravity here for that. You're so far away from the sun, you're not getting enough solar energy to warm up the planet and cause these changes. So So they're trying to figure out now what's going on here, what's causing all this. And what they're beginning to think is there's a liquid water ocean under the surface. So if you look at this picture, there's the heart, there's Charon. Remember, they're in this phase-locked orbit. So Charon is always opposite the heart. And they think that heart's there because of that interaction between the two of them. Over time, the ice plains have formed on that side of the planet. And for all of that to happen, you have to have water underneath the surface for things to move around like that. So you've got the different ices up here, but this section here is liquid water. So here we are, billions of miles away from us, and we're finding water. Liquid water. And liquid water is the ingredient you need for life. Is there life there? Who knows? But liquid water is one essential thing you need to have for that process to really happen. So, people are pretty excited about this. They're trying to figure this out. People are talking about, when are we going back? We got to go back there and figure it out. What's happening? Okay? So, after we flew by Pluto, we went into the Kuiper Belt. And another thing happened while we were traveling these 9.5 years. We found an object that we were going to go by. We didn't know it was there before when we launched. Turns out there's this Kuiper Belt object called Ultima Thule. So we're like, okay, let's keep going and see what this is. On the left is the picture we got. Kind of looks like a snowman, tipped. They weren't sure if the two parts were fused together or not. They now know they are. And then when they did the analysis, it turns out that we're looking at it from the top or the bottom. It's actually a pancake kind of thing. So that's the furthest thing we've ever seen in our solar system. Pretty amazing. So where do we go from here? Well, we're funded through 2021. All the data is still coming back. Through the summer of next year, we'll still be getting data, so we're going to discover a lot of things we hadn't thought would be there. There might be some other Kuiper Belt objects we can go by. We're still doing that dust measurement as we go through the solar system with those 3 instruments. And they even changed the logo. So once they flew past Pluto, they changed it to the extended Kuiper Belt mission. So this could actually continue into the 2030s because there's enough fuel on that spacecraft to keep everything running if we so choose to fund it and keep going. So a couple of resources here if you want to know more. There is the NASA New Horizons website. There's also the Applied Physics Labs website. A really great book. It's written by Alan Stern. He was the project manager for this whole mission. It's called Chasing New Horizons. Great book. There's one written for children age 12 to Pluto and beyond. And there's a NOVA special out on PBS. It's available on DVD, but you probably, I haven't checked, but you can probably stream it as well from a PBS site. So, pretty amazing story. Not yet concluded. So we'll see what the data for the next almost year tells us in the future. So, thank you. And his job is to monitor the orientation of the space station and also to move the space station when vehicles are coming in and going out from the station itself. He also works on the navigation and control systems for the SLS, the Space Launch System, which is the new rocket we're building to take us to the moon and then on to Mars. And he's also working on some of that same navigation information for the Deep Space Gateway, which is a small station that we're going to put around the moon that hopefully will help us have a sustainability on the moon in the future. So it's my pleasure to introduce John.
Thanks for that great introduction. As I mentioned, I'm also John Mackin, and I've been down in Houston, Texas for about 11 years working on mission control mission, and now working development for the next wave of the next 5 years of human spaceflight. So here's a picture of the International Space Station Mission Control. And I sit right here at the Attitude Determination Control Officer seat. Here's my fun NASA official photo. And as my dad mentioned, I make sure that the vehicle is in the proper orientation for the coming and going of crew vehicles and resupply vehicles. When we're notified of some potential collision with space junk, we'll actually move the space station to avoid that. We call it conjunction, when those two pieces come together. I've got to work in Japanese resupply vehicles, Russian crew vehicles. It's really an international endeavor, and it's just been very cool to do that. A few years ago, I started moving on to the next thing that NASA's doing. We mentioned earlier Artemis. This is our return to the moon. And so I'm going to let this short video roll, and then we'll talk about the inner workings of it.
50 years ago, we pioneered the path to the moon. The trail we blazed cut through the fictions of science and showed us all what is possible. Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Spaceflight system, SLS will be the most powerful rocket ever developed.
And with components in production,
And more testing.
this system is capable of being the catalyst for deep space missions. We need a capsule that can support humans from launch through deep space and return safely back to Earth. For this, we built Orion.
This is NASA's next generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources.
We're currently developing an entirely new approach to landing and operating on
So if you want to watch that video again, it is on YouTube. Everything I'm showing you today is available on NASA's public websites. So I'm going to try and tie it all together for you, give you some more detail than that video had, but there's a lot out there you can see. So we talked about the Artemis mission. Basically, there's going to be 3 main Artemis missions. Artemis 1, which is a test flight to make sure the crew vehicle Orion and the rocket SLS are safe and can provide for the crew on their mission to the moon and back. Artemis 2 is going to be the first time where we have crew on Orion. And so they're going to go on a flyby, kind of like Apollo 8. We're on the far side of the moon and come back. Meanwhile, we're going to be building a space station called Gateway on the far side of the moon. And that's where the different pieces of the lunar lander are going to come together. And so by Artemis 3, all of that will be in place, and the crew will go to the Gateway. 2 members of the crew will get in the lunar lander, go to the moon, and then come back. So that's sort of the big picture. We've got a lot of commercial partners. Right now, they're competing in the different parts of the lunar lander. We recently picked the first 2 pieces of the Gateway, and also pictures and some cool stuff about that later. So yeah, basically, let's go here. So here's Artemis 1. That's going to be end of 2020, beginning of 2021. Artemis 2 should be about a year or 2 later, and the goal is to land on the moon again in 2024. And as the Artemis program is going to be 1 man and the first woman to walk on the moon. So that's the big plan. And so you can see, I mentioned, here's Artemis 1, it's a test flight. Test 2 with the crew, and 3 we finally can do it. And so it's going to take all of these different vehicles all working together to make this possible. And my job in mission control is to make sure the operations go as smoothly as possible. Make sure that we've thought of every next burst failure, every bad thing that can happen, and get the crew in place to be able to handle this. So we're going to talk about the different parts, these different vehicles now. So the crew vehicle Orion, we had a test flight of this in December 2014. The mission was called EFT-1. That tested the heat shield and some of the systems. After that, there were some changes made. We invited the Europeans to join us and provide a service module. So the area here in the front, this is the crew module. So that's where the core crew member will sit. And this back part is called the service module. So that's where all the power and all the propulsion and everything they need to keep them going while they're in space is back there. At the conclusion of the mission, just this front part pops off, and there's a heat shield over here, and that's how they re-enter, eventually landing safely off the coast of San Diego. So like I mentioned, it launches from Florida. It takes 4 crew members to the lunar vicinity, heat shield, and parachutes for entry, and it returns in San Diego. So here's a good breakout of the European service module back here, the crew module here, and then this is the abort tower. So the next couple of slides we'll talk about the Space Launch System. But as they're taking off from Florida, if something were to go wrong, this abort tower can pull the crew module safely away from the rocket and protect it. And we just had a test of the abort tower called AA2 in July 2019. So it's very recent. It's a very successful test. There's a really cool video you can watch on YouTube of the test. All right, so that's what Orion looks like. That's what the crew will live in for the weeks of the mission. The next big part is SLS. So this is what's going to put Orion first into a stable low Earth orbit, and then perform what's called the translunar injection, which is the big chemical engine burner that pushes them to the moon. It's 322 feet tall, 8.8 billion pounds of thrust, which is actually more than any of our previous vehicles. It uses hydrogen and oxygen cryogenic propellants, and we'll kind of get a breakdown of how the rocket's put together on the next slide. And we're using a lot of flight heritage. So the core stage is based on the Space Shuttle. The Space Shuttle had 3 main engines. This is going to have 4 main engines. It also has the same, very similar solid rocket motors on the sides. You see that here and here. And you kind of think about this big orange tank. So that was where all the cryogenic propellants were on the space shuttle. That's really not part of the structure in the middle here. And then topping it off around this part is an upper stage, which is based on the existing Delta IV. So that's what puts them on the translunar injection. You can see the height here, so it's kind of washed out, but this is the Saturn V on the left here, so that was the Apollo rocket. It's a little taller, and then you can see the space shuttle's at maybe 2/3 the height. So it is a really tall rocket. It's so tall, in fact, that they can't test the whole stack together until they assemble it in Florida. Let's go ahead here. So this is the liquid hydrogen tank. You can see it's the red part over here. And then this is the liquid oxygen tank, which is over here. So I have seen on a test stand just this tank, just this red part, and it is incredibly tall. And so, part of the test flight is making sure all the parts work together. And it's also why when I put people on the first launch, it's very big. You can kind of see back here, these are the 4 engines. So we call this the core stage, this main part here. And this outside is called the boosters, or the solid rocket boosters, that's what these. So for the first 2 minutes of the flight, these are giving the most of your thrust, and then they fall away once they're pretty much empty. And you can continue using those 4 main engines to finish the ascent. Here's a little bit more on the boosters. So on the space shuttle, they have 4 segments. They added a 5th segment to this vehicle, so they're even taller, they give you even more thrust. But unfortunately, they're not reusable now because they get burned out in the future. But this is a very bright flash you see when the space shuttle launched. It's going to look a lot like that with a little more thrust. Let's see. Okay, so we talked about Orion. We talked about the Space Launch System. This is the mission map of how it all works together. I know there's a lot here, so I'm going to try and talk you through the different pieces. So, starting in Florida here, we have Orion stacked on top of the Space Launch System. It launches. The SRBs come off over here, and then the core stage completes, and the upper stage takes over. It does a small burn here to make sure it stays out of the atmosphere, and then down here on this side, it does the translunar ejection, which puts Orion on this path. It's going to go to the moon. So that launch path. The upper stage is actually also going to go out towards the moon and use that gravity assist around the moon to dispose itself into the solar system. Along the way, it's going to drop off a bunch of CubeSats. So there's a lot of universities that have been able to get small satellites that go out past the moon on this mission. Once Orion gets out to the moon, it actually uses the moon to get into this what's called a distant retrograde orbit. This is a very long orbit that's actually past the moon. And this will give them a couple weeks to check out all the systems and make sure the vehicle's ready to handle the crew for 30 days. At the conclusion of that, it's swim by the moon again, coming out of this purple line, and they will return to Earth. I'm actually going to skip out of the atmosphere once, and then come in and drop their chutes and end up in San Diego. Any questions on the Artemis 1 mission? There's a lot here.
How does actually the rocket make turns and very way?
So the question was, how does the rockets make turns? And you go, oh, that's what we got. Okay. So down here at the bottom, okay. So you see the 4 engines here? Those actually can be gimbaled. And so they move and they use that thrust to change their orientation of the vehicle. When the solid rockets are on, they can do it too. So that's how you go up and turn and then get to the orbital velocity. The question was on reentry, what's the purpose of the skip? And yes, it is to reduce velocity. So they kind of come in shallow, come back out, that slows them down, and then they can slow down more the second time. And then once they get to the right conditions, they can put the chutes out and safely splash out.
So you mentioned the gateway is going to be built during these different launches. Is there going to be pieces of the gateway that are for Artemis 1 and 2, and then they're going to be rendezvous, or how do
Yeah.
they?
So the question was, how are they going to put the Deep Space Gateway together? And those are going to be commercial launches on different vehicles like SpaceX Falcon 9, Falcon Heavy, or Delta IV, or Atlas, and maybe some others. But that's the plan. We'll talk a little bit more about that later. All right. So let's go. Since Artemis 1, this is the test flight. Artemis 2, this is the first time we're going to have crew. So again, there's a little less going on here. There's still a lot happening. So again, we launch here from Florida. See the two the boosters will come on. The upper stage will actually start to burn seconds after the core stage stops to the finish getting in orbit. We'll put the crew on this. It's a 42-hour duration orbit. So it's a very high Earth orbit. That'll give them enough time to check out all their systems, to get a sleep cycle in before they commit to going to the moon. And so they will, upon completing that orbit, they'll actually finish the translunar injection with Orion service module, and that'll go out and do a lunar flyby. And then again, come back, returning and skipping the atmosphere and then landing or splashing out in St. Paul, San Diego. So this will be the first time since Apollo 17 that we have put humans out to the moon, the lunar vicinity. And in the meantime, we should be launching those first parts of the Deep Space Gateway to be able to get ready for the next thing. So let's talk a little bit more about Deep Space Gateway. I think it was mentioned in the trivia question that there's a special orbit. So the gateway is in what's called a halo orbit, which is a special orbit that sort of uses the Earth gravity, the moon gravity, and sort of constructs a weird shape. And it's kind of hard to describe. I think the best thing we can do is actually show the video of it. So this circle is the shape of the orbit. In the back there, you have the Earth. And around the top of this loop is the moon. And so this is about a 6-day loop. And so this is a sort of an interesting low gravity area where we can kind of store things and put together our lander. Originally, a lot of the research for this was looking to Mars. So this is a good place to put something before you send it to Mars. And down the road, when we're regularly landing on the moon and we're using that water ice, we could actually refuel things here before they go out into the solar system. There's a lot of other things that will be, after 2024, there's a lot of advantage that happens here. It's also a good place to basically return your lander to and then reuse it. Which, on this first set of missions, there's not going to be a lot of reusing, but long term, that's the goal to make this sustainable. So we can have people on the moon regularly and not just sort of political stuff like Apollo was in some ways. Alright, so here's a picture of the gateway with the lunar lander and Orion. So Orion's over here, and the moon's down here, Earth's right there. And so we have a lunar lander attached to basically this power propulsion bus. So it's got 2 big solar arrays, it's got different kinds of chemical propulsion and electric propulsion. And then this is a mini hab. So a small habitable volume that the crew can use to get ready for their lunar landing. Also shown in the picture is a logistics resupply vehicle. It may or may not be there at the time, but they are going to have resupply available there. So the lander will be completely out there. We will launch Orion on a quick run if we get to it. And this picture is kind of hard to see. This is actually from the request to the companies to try and build the parts. So basically multiple launches put the lunar lander out of Deep Space Gateway, then Orion launches an SLS and rendezvous with that. The 2 crew members get in the lander, go down to the surface, and do their surface mission, while the other 2 astronauts stay at the gateway. And this is kind of like, Apollo 11 does all during Neil Armstrong went to the moon, but Michael Collins was stuck in the crew module waiting. Actually, I got to see him talk recently, which is very cool. And he had all these contingencies he was ready for in case the ascent didn't go well, in case the crew, Neil and Buzz, couldn't get all the way back up to him. And that was really, people have been asking for 50 years, like, oh, what were you doing, what were you thinking when they landed on the moon for the first time? And he said, I was focused on the next thing, making sure they got back safe. It was a pretty dangerous thing. It's still, the spaceflight still is dangerous. Another interesting thing about Apollo 11 is Nixon actually had a speech ready in case Buzz needed to go back for his moon. It was released on the Freedom of Information Act 5 years ago. My job as mission control is keeping them safe. Hopefully, I don't want to get too far down this path, but that's what we do. We're going to send these people in this dangerous environment, and we're going to bring them back safe. So after their foray on the moon, they'll go back to Gateway, and then everyone will come home real quick. So that's sort of the big picture of how Artemis IV is going to happen. So we got one more slide. And here we go. Landing near the South Pole, because that's where the water ice is. The crew's going to come down in the lander, but we should already have some resources available to them from robotic missions. So they should come with a rover or a robotic helper or some pre-station supplies if need be coming in with us. So any questions on Artemis IV?
So the gateway will be assembled in Earth orbit by astronauts and then moved to the Halo?
No, actually it's different. He asked if the gateway is going to be assembled in Earth orbit and then moved out there. We're actually going to launch the different parts separately, and they're going to meet up out there. And as part of it, that first power propulsion bus with big solar arrays, that's actually going to be owned by a contractor, and they're going to put it through its paces, and it takes, they're going to use electric propulsion to put it out there about 180 days, as opposed to like 3 or 4. And so once they've shown NASA that this thing is going to work, then NASA will basically buy it from them, and then start adding parts to it out there.
How will they be added to it?
Yeah, so they'll have their own propulsion systems, and they will dock out there.
Robotic?
Yeah, robotically dock. Yes, that's going to be done. We do some of that now on the space station, but most of the space station is built with astronauts' hands and the space shuttle robotic arm. So they can't be, the modules can't be as large, right? But they're going to have their own systems to get there. No, we have a couple astronauts that are just for generically working exploration, and as things get closer, they'll tap. I think, I'm trying to think, we've got a couple other crew vehicles right now, and they've only, they're supposed to launch in the next year, so they're only recently tapped those crews, or at least announced the full crews. There's a couple people working it at all times.
The primary landing site right now is the South Pole.
Yeah, the South Pole. So I don't have a map of this, but if you look at all the Apollo landing sites, they're all near the equator. And that's an easier thing to do. It's still a little hard. But yeah, so one of the requirements was be able to go anywhere in the moon, not just those equatorial regions. And then when we discovered water ice, it was like, well, that's what we want to focus our energies. Okay. Well, thank you so much. I hope you have a better understanding